Welcome, folks. I want to introduce rings mainly by contrasting them to fields at first. So a field was a abelian group under addition that was equipped with multiplication that formed an abelian group after you removed the additive identity 0. And you also had this distributive property. So I've written down all of the properties of fields right here. Fields included things like the real numbers, the rational numbers, the complex numbers, and z mod pz for p a prime. Z mod nz for n not a prime was not a field because you didn't necessarily have multiplicative inverses. Rings are more general. Every field is a ring, but not every ring is a field. Rings will furthermore include things like the integers, or z mod nz, where n doesn't need to be prime, or the collection of all n by n matrices. So let's chat about these briefly. Why are these not fields, even though, as we'll later see, they are rings? So in Z, the element 2 has no multiplicative inverse. Sure, 2 times 1/2 is equal to 1, right? So 1/2 is sort of a multiplicative inverse for 2, but 1/2 is not an integer. Okay. Similarly, 3 has no multiplicative inverse. 4 has no multiplicative inverse because 1/3 and 1/4 are integers. So the only elements here that have multiplicative inverses are 1 and -1. And that's why the integers are not a field, right? In a field, every non-zero element has to have a multiplicative inverse. Similarly with z mod nz for n not prime, that's not a field. So let's look at z mod 4z. All right, does 2 have a multiplicative inverse? Well, 2 times 0 is equal to 0, which is not the multiplicative identity 1. And 2 times 1 is equal to 2. And 2 times 2 is equal to 4, which is 0. And 2 times 3 is equal to 6, which is 2 in z mod 2z. So we've seen here that 2 has no multiplicative inverse because I never got 1. Okay. So since 2 has no multiplicative inverse, z mod 4z can't be a field. And let's talk about matrices. So when we're talking about matrices, we always look at square matrices of the same size. So maybe let's look at 2 by 2 matrices. Okay. Let's look at this matrix 2, 2, 4, and 1. Okay. This has determinant 2 times 2 minus 1 times 4, which is 4 minus 4, or 0. Okay. This is because this matrix has 0 determinant, that means this matrix is not invertible. So this matrix has no multiplicative inverse, right? So 2 by 2 matrices can't form a field because here's a 2 by 2 matrix that has no multiplicative inverse. It's not invertible, meaning I can't multiply this matrix by any matrix to get the identity matrix. Here's the 2 by 2 identity matrix, which is the multiplicative identity in this ring of 2 by 2 matrices. All right, well, right now I'm just talking about rings before I've even defined them. So let's define what a ring is. A set R is a ring if it is equipped with 2 binary operations, addition and multiplication, like a field, such that for all elements A, B, and C in our ring, we have the following properties. So we want associativity under addition and multiplication. We only require commutativity under addition, okay? So fields were also commutative under multiplication, but rings don't need to be commutative under multiplication. And an example of that is matrices. When I have matrices, matrix A times B is not necessarily equal to matrix B times matrix A. Now we do have an additive identity called 0, and anything plus 0 is equal to 0. We don't necessarily have a multiplicative identity, okay? That's not required for a ring. We have additive inverses. So for every element A, there's some additive inverse negative A, where when you add A with its inverse, you get 0. We no longer need multiplicative inverses as we had for non-zero elements in a field. Okay, and we do have the distribution rule. Now, since multiplication is not necessarily commutative, we actually have to write down the distribution rule twice, both specifying what A times B plus C is and specifying what B plus C times A is. A shorter definition of a ring would be a ring is an abelian group under addition. So that would be, yeah, addition is associative. It has an additive identity. We have additive inverses. That's what it means for us to have an additive group. And then this means we have an abelian group under addition. Okay. So a ring is an abelian group under addition that also has an associative multiplication. That's right here. That distributes over addition. That's his final property. Public questions so far? Let's look at some examples. So any field is a ring simply because we sort of took the definition of field and crossed out some requirements. And that left us with the definition of a ring. There are still very common things that mathematicians work with all the time, though, that are rings but not fields. So the integers, okay? You have addition, you have multiplication. Both addition and multiplication are associative. Both are commutative, even though we only needed addition to be commutative. But when multiplication is also commutative, as it is in the integers, you call that a commutative ring. Yeah, every element has an additive. There's an additive identity 0. Every element has an additive inverse. So the inverse of 17 is negative 17. And certainly you have this distribution property. Okay. Z mod NZ is a ring. You can distribute in Z mod NZ. You just don't necessarily have multiplicative inverses, but that's okay for a ring. A set of all n by n matrices, which is sometimes denoted M sub n of R. So the set of all n by n matrices with coefficients in R, that's a ring. Now here, we don't have multiplicative commutativity, right? You know, if I write down 2 arbitrary matrices, unless I'm super unlucky, if I multiply these 2 matrices, that's probably not equal to what I get if I multiply them in the opposite order. Okay, so we don't have commutativity under matrix multiplication, but still this forms a ring. It's an algebraic structure that is very well studied. Last thing I'll say in this video is, okay, now some people do require rings have multiplicative identities, but some people don't. So far, all of these rings I've listed do have multiplicative identities. 1 and 1 are the multiplicative identities in Z and N mod, Z mod NZ. And in matrices, you have this identity matrix. What's an example ring that has no multiplicative identity? 2Z, which is the set of all even integers. Or, 17Z, all of the integers that are divisible by 17. Those are rings. You have associativity, you have under addition, it commutes, you have an additive identity 0, you have additive inverses, just take the negative. You can multiply, and multiplication distributes over addition. Those are rings, but they have no multiplicative identity, right? 1 would have to be the multiplicative identity, but 1's not in these rings. Now, just like we learned all of these theorems and properties for groups, people study all these theorems and properties for rings. There are subrings, as we'll see in a video later today. You look at quotient structure. So one ring quotiented out by some subset, which is called an ideal. You look at cancellation properties, et cetera, et cetera. We'll end there with that introduction to rings. Any public questions?